Right, kia ora everyone. I'm just getting set up to make this video going through titration curve medium 2. I have placed this sheet on the Google Classroom, so have a look for it. It's just been posted. So let's read through the question first. We have to do a full titration sketch of the change in pH when we start with 0.232 moles per litre HCl. And we add that to 20 mils of 0.232 moles per litre NH3. We're given a Ka for NH4+, and here's our graph made up for us. Just note there's an error here, so I don't know why, but on my screen this didn't come up, but it's supposed to be the HCl, not the NaOH. Okay, so just in case your sheet's got the wrong thing on it. Okay, let's take a look at what we can see from the question. There's a couple of really important things that we can have a look at first. I'm just trying to grab it. Okay, so the first thing is we need to identify that this is a strong acid and this is a weak base, right? So we're doing a strong acid, weak base titration. Another important thing to notice is that the concentrations are the same. This is 0.232 and this is also 0.232. That means that this is going to be a little bit more straightforward than it would otherwise have been. So that's pretty cool for us. Okay, so let's just now think about what's actually happening in this titration and what we're going to expect. So just remember, a titration, you have got a flask and you've got something in it. In this case, we're adding the HCl to the base, the NH3. So in here must be, 20 mils of NH3, and that is 0.232 moles per litre. We will have some kind of indicator, which we haven't spoken about yet, and then we have our burette. And in our burette is our HCl, and it is 0.232 moles per litre. And a titration is going to occur where we add the HCl to the NH3, and we get to the point where the same number of moles of each of those has been added. Now this will be indicated to us by the indicator, but we haven't started to talk about indicators yet in class. So the first thing I always get students to do is write an equation for what's actually happening in this titration. So in that case, it is NH3 plus HCl. So a single arrow for our titration equations. And we've got an acid and a base, so it's a simple proton donation. This one's a little bit different because you can't easily see how you make salt plus water. Don't worry about that too much. And we are going to get NH4 plus Cl minus when that proton moves. Just double check there that everything's in a 1-to-1 mole ratio, because that's always what is going to happen. Okay, so that's step 1 done. Step 2, right, we want now, so that's step 1. Step 2 is to calculate the pH at the start, i.e. the pH in the flask above. Okay, so that's up in here. So in this case, it's a pH of 20 mils of NH3. So in this case, it is simply a weak base calculation. Okay, so we're expecting on our graph here that we will get a weak base pH. So I'm expecting somewhere around 9, 10 or 11. Always good to have a little prediction in case you make a silly error. So weak base, we need a Kb expression for our weak base. So remember, this is a dissociation constant. Okay, so that's going to tell us how weak our base is by how big this is. We don't have a Kb, so we need to work out the Kb. So Ka times Kb equals Kw. So therefore our Kw divided by our Ka is going to equal our Kb. All right, so that is 1 times 10 to the power of negative 14 divided by Ka over here. 5.60 times 10 to the negative 10, and that gives us our Kb. And I have just calculated that, so just hang up a minute so I don't have to tippity tap. Sorry about all that. And our Kb is going to be 1.79 times 10 to the minus 5. Now that I've got a Kb, I need a Kb expression. So my base is NH3, and Kb and Ka is reacting with water. It's a weak base, so it's an equilibrium. And I'm going to accept that proton as such, and then my Kb expression equals, okay, over NH3. And then I'm going to substitute in my values. So I can substitute in my Kb here. I'm going to make the assumption that these are the same, x times x. And my concentration of NH3 is here, 0.232. Right? So if I make those substitutions and solve for x, that's going to give me my OH minus. And then I need to negative log that and subtract it from 14. Right, and that gives me my first answer of 11.3. Right, so that tells me all that work, quite a lot of work there. That tells me that before I start titrating, that the pH in here is going to be 11.3. So let's just plot that on our curve right now. So I'm just going to bring this over here. Okay, so at 0, I'm going to go up to 11.3, and I'm just going to pop that little cross in there. Okay, that's the first one. Right, so what I like to do next is I like to work out the pH of this thing here. And that gives me my theoretical pH at the other end. In this case, remember, since we're starting with a base, our curve is going to come down. So I'm looking for my theoretical minimum in this case. So let's actually have a look at that now. That's my 0.4. I usually call that 0.4, but it doesn't really matter what you call it. So it's the pH of the other stuff. So let's pretend we've got the pH of this stuff here and we haven't actually added anything to it, right? So it's just the pH of a strong acid. So if I've got a strong acid of 0.232 moles per litre, I know it's fully dissociated, and therefore the concentration of H3O plus is actually 0.232 moles per litre. Therefore I can simply negative log that. Negative log of 0.232. Okay, and I just need to grab my calculator to do that. Negative log of 0.232. Okay, and that is 0.635. I need to ask myself, is that about right? And I've got a strong acid and it's reasonably concentrated, so I'm quite happy with that number. So let's plot that now. Bring back my paper here. It's going to be a bit messy, sorry, because I'm trying to hold my phone at the same time. So here's my 0.635 about here. Usually I would use a ruler, but I do not have 3 hands. So this is my 0.635. And so this is like an asymptote, if you're a mathematician. So the pH is going to tend towards this because we're adding it, but it's never going to get there. And it's never going to get there because we're taking our HCl and we're adding it to something else. So even if I added 500 mils of HCl, I'd still have 20 mils of something else. So it can never quite reach the theoretical pH of the HCl on its own. Okay, so that's my first 2 points done. Now I'm going to calculate my 2 tricky points, and I'm actually going to split this video off into 2 parts. So I'm going to say enoho rā now, and then I'm going to come back with the second video. So we'll see you in just a moment.